الو دكتور جاني.
السلام عليكم.
عليكم السلام دكتور.
عليكم السلام ورحمة الله.
دكتور.
بلى. نعم.
دكتور سعد.
بلى.
من سؤالك هاي.
بلى.
دكتور أو correlation أو سؤالتك correlation the sperm chicken on person data skewed يا تدا هاي يعني نا normal distribution عادي.
Not normal. If you test the data, well, really, I don't know. Yesterday, Dr. Burhan said to me the data are normal, but really, if you test the data really with this test really, you find they are not normal really. If you test this يعني the data.
مش يصير. أنا دكتور أنا شفت نفس الشيء إنه data بيها skew يعني ما.
Yes, they are not normal.
يعني.
Yes, whether the outcome or the exposure, both of them are not normal. So I don't know why Dr. Burhan tomorrow yesterday said they are normal. But I think it is better to use sperman really. sperman would be better.
أنا استعملتها دكتور لأن سويت هيستوغرام.
Yes.
يعني طلع بيها انحراف.
Yes.
يعني
true.
ما كانت.
And if you test really also if you test the data by this test really, well I have to share screen really. Let us share screen. So if you test really test the data really by this one, by this test. So you can put here really the test which you want to put them here. For example, this one. I'll remove this. I'll remove this. And for example, I'll test this. It's for distribution. I'll say run, and then give me. It will give me the result now. It will give me the Smirnov-Kolmogorov test. Well, this is it will give me. So this is really the test and said reject normality. So really, if you do this for our data, to reject normality. So you see that the data are not normal really. So we use this test really to reject normality to see whether the data are normal or not. And I think the lead data are not normal. Therefore, it's better to use sperman. Well, whether use person or sperman really usually will not produce that difference really. But scientifically, we should use sperman. And sometimes there is a difference between them. The result may differ. But really, I have seen that in most of the cases, really, if there is correlation, it will be by person or sperman, it will be the same. And if there is no correlation, it will be the same usually. But really, if you publish your article in a journal, they will ask you whether you have tested for normality, and whether if your data are not normal, you should use have used sperman rather than person, rather than R. And sperman usually is used for the non-normal data. Yes, I agree with you. It is better to use sperman. Yes. So really sperman. With the sperman, you cannot. The problem with the sperman is that you come to graph the data really, and well, you cannot graph the rank data because sperman depends on ranking. Really, next week we'll take the non-parametric test and we'll see how they use the rank. And when you draw the rank data, it not be relevant to your research. So usually the problem is that you have to draw the original data by a scatter diagram and also use sperman, which is really a problem because you are using sperman at the same time you are drawing the original data because the rank usually is not relevant. This is a problem really which I faced here. Because you are using sperman and drawing the original data, not the rank, which sperman use. Really, next week we'll take the non-parametric test next week. But today, really, I don't know if you have another question. Does any of you have another question? Really, if you don't have a question, I would say today we will have, and according to our course, we have here really, we should have survival analysis today, survival analysis. And next week probably will be the last one, non-parametric test, will be the last module, non-parametric test. So we'll talk about Spearman and Pearson next week. We'll talk about Mann-Whitney test, Wilcoxon rank, Friedman and Kruskal-Wallis. We'll talk about them next week. But today we have survival analysis really. Last week was logistic and linear regression. So today we have survival analysis really, because survival analysis we are not going to go into detail really. I think we have time to probably talk about sample size. So really, I think someone really asked me about sample size, survival analysis. I will show it to you after I will talk about sample size. I think Dr. Manhal asked me about sample size. Really, in SPSS, really the standard module, the standard SPSS, does it contain a sample size and power sample size? Does it contain really? The program for sample size, power sample size, is really a separate program, separate module or addition, or called extension, I think. So really, I have it. A sample size, the power sample size, SPSS, I have it really, but really it is not that simple. And also we have also NCC pass. Pass means power and sample size, also very famous. Pass also I have it really, but really again it's not easy really. But I have found easy program to estimate sample size, sigma plot, stata, midcalc, and minitab. So there are really several program which estimate sample size and without additional module, without additional program. And inside the program, inside the software itself, there is a sample size. Sample size, for example, stata, to see stata 15, and here of course there is really, you can sample really many types of study. Really take time really to open because there are too many selection. As you see, there are too many things you can do a sample size for it really, and there are too many things really. We cannot all and go into all of them really. Probably you can go to this one, for example. This one probably, well, again, not that simple really. It is not that really, it's complicated really, I think. Let us see something that's simple in order to show to you just an example. But really it has many examples. Just comparing two independent means. Well, for example, this one again. Well, this one is very simple. This is similar to Z-test really. Very simple. Okay, it's simple, very simple. Sample size. Well, we have, of course, really he's put default is that put the significant level is 0.05. You can change it, of course. Of course, decreasing this and make it 0.01 will increase the sample size. 0.01 or 0.02 will increase sample size. Power, again, usually put the power as 0.8 or 80. We can make it 0.9, but that will increase the sample size really. So default usually is 0.8. Usually the acceptable power level is 0.8 or 80%. And the acceptable significant level is 0.05, 5%. Now, we should really, the standard deviation, we have put the standard deviation. So this is difficulty. You have to have information about your study and priori. Before you have done your study, you should know, you should have idea about standard deviation taken from another study, from a pilot study, from a preliminary study, or from pilot study, small study done at the beginning, or from other study and in the literature. And so suppose that probably we have the test in the done the Z test in the example for the which I have done in the master degree, or I'm giving them now in the master degree. We have the Z-test, for example. We have a null hypothesis of, we have the prothrombin level in the population 18.5, and suppose that in the we expect that the no, it's 20, real 20, the population 20, and we expect that it will be 18.5 in the sample. Suppose that a pulse study, and standard deviation, suppose it's a 3.5. Suppose that we want a sample size that detect a significant difference with the null 20 and with the estimated X bar or mean in the sample 18.5. It's estimation, of course, either taken from other studies or from a pilot study. And it's also estimation taken, and this is not, we don't know, we want to know the sample size so that we do our study, but now these are estimation. Of course, if you don't know these, you should go and find them in literature, in a similar study in your country or in neighboring country. Usually, again, we select two-sided tests, and we don't use the population correction, which means the population is very small. Yeah, don't use this. So you say okay, and it will give us a result in state. That is a result. So the sample size really is 45, and the sample size sufficient to discover a significant difference is 45. And really, if you come to the Z-test, really you find that they have taken. If you come to this, I'll give you this. Really, I think I give you this in a master degree, the Z-test. So really, they have used 49 sample size of 49. Even if you use, and they have reached a significant difference. Really, the result was significant. Really, so really the result was significant. Really, so even if you take 45 according to our sample size estimation, if you take 45, the result again will be significant. Probably it will be 0.05, but it will be significant. So this is really the sample size required to obtain a significant difference with this mean and mean of the population and sample and mean of the sample mean of the sample. So you go like this, yani. So you have to have information. Yani really, without information, you cannot estimate your sample size. Now let us go to this. We have this is what is called two per test, or two independent sample, or what's called the independent t-test, test for two sample mean, test for two sample. Again, you have estimation about the sample mean in both sample, really, and you have to estimate priori, and before doing the study, you should have estimation of the mean of the sample. And again, we have estimation of the standard deviation, whether it's common or separate standard deviation. And then we go and press OK. So really, it is not easy. And if you don't know the mean, you cannot really. And also, you have the idea of about estimation. You have estimation of samples of standard deviation. Without it, really, you cannot estimate the sample size. Okay. So really, sometimes we have a privilege study. Commonly, really, in epidemiology, we have a privilege study. I mean, you want a prevalence of disease, or you want to study prevalence, for example, of anemia, of influenza. So you want a sample size. You want to estimate, for example, prevalence of tuberculosis, prevalence of malaria. So in this case, really, for our we use a frequent an equation, a famous equation, really. I will close this data, really. So I will show you the equation, really, which is really not that difficult, but we use it frequently. and it is really some students really they are using it when they do prevalence. For example, a PhD of Dr. Hoger, for example, about the prevalence of delay in tooth eruption. We use this equation. Dr. Ari, Dr. Berivan, there are so many. Dr. Fadwa, many of them really use the this equation really, which really I'll show to you in one of my articles, which are present in the internet. Let us see this one. Well, I want that. I'm seeing for the article. Yes, this one. So this is really an article, but the equation used frequently in the literature really. So this is about this is a study about family planning, unmet need. So really we use this one, this equation or this equation. So this equation, which is really not that difficult equation, very simple equation really. So here P really is n sample size, and P is the prevalence, yani, which is estimated prevalence. So we should have idea, just like in case of the t-test or ANOVA, we should have estimation. So here we estimated, we should have idea about what we will find, what we will find in the study. And Q really is 1 minus P. Z really is 1.96 or 2 squared, 1.96 squared. D really is design effect. I will talk about this. Sometimes we don't use it really. And divide by E. E usually is the standard error, which is usually 0.05 squared, 0.05 squared. So prevalence usually, when I want to take the maximum sample size, I use a prevalence of 0.5. So if I don't have a study, I will use 0.5. Now Q will be of course 0.5 again. So if the prevalence I use is 0.5 or 50%, then Q will be again 50% or 0.5. Now Z is really is 1.96 or 2 squared. Z terbiya. Now design effect is usually something complicated really, but usually when I take a sample in the city, they are homogeneous population, so I don't use design effect. But when I take the villagers, yani urban area and urban area and rural area, I usually multiply by 2. My sample I multiplied by 2. And E is the expected standard error, usually 0.05. Really, when you do this equation without design effect, it will result about 390 or something, almost 400. So usually, many study they use 400, like Dr. Fadwa, because the study was urban. The study was an urban area. When the surveyor like Dr. Ari, Dr. Berivan, or Dr. Hoger use urban, the sample, the study use urban and rural area, he multiplied by 2. So his sample will equal 800, almost to 800. Like in this study, the sample size was 800 or 801, etc. It's 800 really, 800. So this equation really even can be simplified really. So this is the prevalence, and this is the 1 minus prevalence. This is Z, we can say 4 simply, because 2 or 1.96 squared, almost 4. We can sometimes remove the design effect. There is no design effect sometimes. If you take a homogeneous sample, as our sample is only in the rural area or only in the city, so we don't need design effect, and divide by E. Of course, E here really is 0.05. But if you want to take a larger sample size, you decrease this. You take, for example, 0.03. Your sample size will be about 1,000. 0.02 will be even more than, probably to be 1,300 or up to 1,500. So really you can increase sample size by changing the accuracy. And if you want a smaller interval of estimation of the prevalence, more precise estimation, you decrease you decrease the standard error, and of course you need more sample size. So this is really, we use this equation frequently. I mean, this equation, which is simply PQ multiplied by 4 over 0.05 squared. 0.05 squared. If you want to increase your sample size, make it more accurate, you decrease the 0.05. You make it 0.03 or 0.02 or 0.04. That will increase your sample size, but of course, make your study more difficult. But of course, the precision will be better. Yani, your study, the result will be more precise. Okay. Of course, you can do all of this, yani, and with sigma plot, with stata, with midcalc, with minitab. Really, there's another program called StatDirect, really even more simplified, yani. And there's also any query. There is also yani, a free program, OpenEP. There is open program or free program in the internet, which you can use again to estimate sample size. Okay, this is just an idea about sample size. Really, sample size is still a challenge. Yani, even when we took this, when we are student, really, it was a challenge for us. And because the equation are very complicated. Yani, if you want to, really, as we said, this is a simple equation. But when you come to t-test and ANOVA, and without a computer, it will be very complicated. When we have a clinical trial, ANOVA, Ness of variance, Fisher exact test, and chi-square test, really the equation will be more difficult. Yani, and I think probably Dr. Kaiser also will talk about this, about sampling, about sample size. Really, it will not give you the software, but we can use really any software, and whether it's free or commercial, like this software. Really, I find it more easy even to use StatDirect, what's called StatDirect. But the version really of StatDirect I have really is on old version. But certainly Minitab contain midcalc, sigma plots, stata, all of them incorporate sampling size yani estimation. While SPSS really it have a separate program, a separate module for which you have to buy yani, or to install in order to estimate the sample size. Okay, so as you see, sample size need information, and without information, we cannot estimate the sample size. We should know, we have prior information about the sample size, about the prevalence. And of course, here we use 0.05, which gives us the largest sample size. But usually, yani, the purpose of sampling size estimation is to have the smallest sample size, so that you do a study with the least expense and least danger, least discomfort to the patient. So you should really obtain the minimum sample size to obtain a significant result. But really, because here we are doing a prevalence study, which is usually a questionnaire, there is no harm to the patient really. Therefore, we can really take the largest sample size, which is obtained by putting the prevalence as 0.5. So the prevalence is put 0.5. Of course, if it is 0.4, the sample size will be less. If it is 0.3, 0.2, the sample size in this case will be less really. In some epidemiological book, you find a table really, which give you the sample size for the prevalence study, or for the study, a cross-sectional study. Well, there is an old book, Epidemiology for District Health Management, of really the version is 1988. You can find it, it's free of the internet. On AWO site, you can find this book, Epidemiology for District Health Management. It contains a table at the end of the book, contain a table which really use this equation for different precision. Use this equation for this different precision and give you sample size. You don't need to calculate. They simply give you the sample size already calculated. Really, the book is a famous book called classical book, but there is no new version of it. It's called Epidemiology for District Health Management. Okay, I think it's a sufficient idea about the sample size. Still, I agree that sample size estimation is not an easy process. Now our subject today, as we said, is survival analysis. Survival analysis. And survival analysis really is in survival analysis really we have another type of data. We say the type of data are four: nominal, ordinal, and we say also discrete continuous, discrete numerical, and numerical continuous. Numerical continuous. But here there is another type of data called time series data or longitudinal data. Really, the longitudinal data contain two columns, not on one column. Contain the time and the event. So this is called time to event data, or survival data, or longitudinal data, or time series data. Really, they contain two columns. So the data really is time until occurring of an event. For example, in this example, we have time until remission. So the time the patient, we have patient with cancer who were given two types of treatment. So the group can be more than two really, but here we have only two groups. So first group were given only chemotherapy. Second group were given chemotherapy and radiotherapy after breast cancer surgery, etc. So this is or after chemotherapy for lymphoma or prostate carcinoma, whatever it is, they have given treatment, and then we record the time until remission. So until the patient is cured or remit, so this is time until remission. Sometimes we have time until death. So death usually is not favorable outcome, but here we have a favorable outcome. Really, we have remission, which means that the patient go into remission after chemotherapy, and he become as if cured, cured. So time until cure or remission. Sometimes we also calculate the time until death, or we give him a drug and time until having a disease. As we see in Dr. Amin data, the patient, they have given a drug, aspirin, etc., and then he recorded the event until the time until they have myocardial infarction or angina, until they have unstable angina or myocardial infarction, جلطة قلبية. So really, here what we should have in survival data, we have the time and we have the event. So suppose the study is 3 years. Okay, suppose the study is 1 year or 3 years. Sometimes the study may be 10 years. So suppose the study here is 3 years, and we are writing the time in month, really, month. So when the event occur, we record as 1. So it is remission. Okay. So remission is 1, and no remission is 0. No remission, so he remained ill. But of course, this is what's called a censored data. So I mean, at the 9 months, the study was 3 years. So at 9 months, really, this patient was lost to follow up, or maybe died of another reason. So this is called censored data. So really, he was not remitted, but we really at 9 months we don't know really he was lost to follow up. Probably later on he go into remission, but we don't know. So his data is cut or censored. Censored means مثلا مقص أو تقص data. So this is called censored data. Sometimes really we reach the end of the follow up. So for example, we reach to the end of the study. Almost we reached 3 years, and with the end of the study, the patient doesn't reach the outcome. Let's see, we don't have probably the follow-up until 35 years, until 35 months. So at the end of the study, really, almost 3 years, the outcome was not really, the patient didn't remit or didn't develop remission. So again, this is censored. Probably later on, after 3 years, he developed remission, but we don't know. So again, this is censored data. It's called censored. So then we have two type of censoring. Censoring when we don't know that we lose the patient, we don't know what has happened to the patient after a certain period of time, or when we reach to the end of the study and the patient hasn't developed the outcome. So this is called censoring. While these are not censored data, those who reach the outcome, these are not censored because they have reached the outcome. They have remit. So this patient, for example, after 1 month, he reached remission. This patient, after 10 months, reached remission. This patient, for example, after 22 months, reached remission. Okay, well, this was censored. So then the characteristic of survival data is that contains censored data. Censored data. So censored data really can be arranged into a life table, or not take real life table. It's a big subject really. Used in demography, المسكان, we use life table, but we can't really use a survival analysis really in SPSS. Really, if these are not two groups, we can just draw them. We can draw the survival curve for this patient. Now I will draw the survival curve. I will go to survival. Okay, I will not use life table because it's more complicated really. I will use a Kaplan-Meier curve. I will draw the really the time. This is time, and the status or the outcome, and the event really is 0, 1. It's a single factor, only 1. So 1, and this is the survival or remission is 1, and no remission is 0. So now really I don't have factor here. I think option will tell us about plot. I will draw the survival curve. Okay, so to see the curve really. So this is really the survival function of both groups really. Okay, both groups. Okay, so these are time enter remission in both groups really. I as if I am drawing the both group without differentiation whether they have taken chemotherapy or chemotherapy plus radiotherapy. So this is the survival curve, you see. So these are the cumulative survival. So as we go into time, the patient who don't remit become a few. So these are remitting. These are going into remit. Whenever patient remit, it will go. Of course, we have a step down. So really, these are really we reach here, and they haven't really reached to remission. And these are the censored, of course. These are censored patient. So this is what happened to them really. And as the study go on, of course, the probability of remission, of course, increases, or the probability of remaining in non-remission decreases. Okay, so it's complete survival, and the probability that you will not remain in remission, you will not go into remission, decreases. Okay. Now let us remove this and let us analyze them as two groups. Really, I've already analyzed this, but I will show to you how I did it really. What I go to survival, to Kaplan-Meier, but I enter a factor really, the group here. So they are here. The group really is either chemotherapy or chemotherapy plus radiotherapy. And I will take also log rank test. I will do a log rank test. I compare between the survival of the two groups. Okay, so again, I will say survival curve. Let us see what will happen here. So it really give us the, so there are 21. So 21 patient, all of them, they are 42. So 21 patient took chemotherapy. I think it's lymphoma, really, lymphoma. 21 took chemotherapy, and 21 took chemotherapy with radiotherapy. And these were not useful, this table, but probably this table is useful, really. So this is the time until remission. Of course, here we prefer a shorter period because the remission is a favorable outcome. Of course, when the outcome is death, really we prefer a long duration. Yani when, for example, the outcome is death, which is usual in survival analysis, I prefer the outcome to be, yani the duration to be longer. But in this case, really, the outcome is remission, a favorable outcome. So really, a favorable outcome is shorter duration. So the estimation of the mean looks, those who took chemotherapy and radiotherapy go into remission more rapidly go into remission. While chemotherapy, they delayed really. And again, the median, again, the same thing. Again, the median and this is the mean and this is the median. And we compare them by log rank test, really, log rank test. We cannot compare them really by logistic regression or by t-test, really, because there is censoring. If there is no censoring, we can compare them. We can compare the mean by t-test, by t-test, or by, we can also use Mann-Whitney, for example, compare the to median, non-parametric test for the median. But because censoring, we cannot use the usual statistical test. We should use a test which take into account the censoring of the data. So when do log rank test, really, it give us significant results. So I mean, there is a significant difference between the two groups. And this is the drawing between of the two groups. As you see, those who took chemotherapy plus radiotherapy, they spend less time. They remit rapidly, more rapidly, while this delayed, the remission was delayed, and some of them really didn't go into remission. So these are the those who took only the chemotherapy. So they remain without remission for a longer time, while those who took chemotherapy, they spend less time until remission. Okay, so the remission was better. So taking chemotherapy plus radiotherapy is better, and there is significant result. Okay, so this is survival analysis. Okay, really what we have studied really is the effect of only the chemotherapy and radiotherapy, only the effect of the drug or treatment. But however, there are other factors may be considered. For example, the age, the stage of cancer, probably anemia, whether the patient have anemia, their weight, we don't know. So there are other factors really which may affect the survival. So really this is done with Cox regression, with Cox. So there's another analysis here, it's called Cox, really Cox. So in Cox regression, really, we also enter time, the same thing here. And also we took the status here, and also we defined as one here. But of course, here I should enter the covariate, the factor which I believe will affect the not only group, but also there are other factors, like for example, the stage of cancer, stage of the lymphoma, etc. So Cox regression really is just like regression for survival analysis. It gives us the relationship between survival and the factor which are believed to affect the survival. So I'm just going to show you an article. I think it's a published article by Dr. Amin, the physician, Dr. Amin Musa, just to show you how to put it in an article. or how to do Cox regression, how to do also how to put the result of Cox regression and survival analysis in an article. Let's go to medicine. What is medicine? Medicine. And Dr. Amin, and with, of course, with the genius Dr. Nasir, of course. I think so. This is the I think this is the survival. This is a Kaplan-Meier. These are let's see whether I'm not sure here the survival data or not. I don't know that it's really. These are all the data really, which I mean, well, this is really so this is really survival, yes, and this is time month, and this is so the enzyme really they have divided according to an enzyme or level of enzyme. So this is the outcome really, the outcome of this. This is a long run test significant really. So this is a probability of survival. I think I'm not sure of the enzyme, but there's an enzyme here. What is the enzyme really? I don't know. But the MACE really is a occurrence of event of myocardial infarction or myocardial infarction or angina. But really, I'm not sure of what is the division was according to what really. I'm not sure. So really, let's go to the material method present here. Probably according to this enzyme. Probably he divided them into this enzyme, and then he showed the survival in months. Okay, and this is a long rank test. But I think he didn't use here the Cox regression. I think there's another article which he used Cox regression, but I'm not finding it. I think this one, or it's probably this one, or this one, yes. So this one, Plavix really. So Plavix, and where's the article? To see the article. Really, I have the article really. I think the article. Probably this one. So this is you see, this is the longer test really. Really, this is aspirin resistance. Really, here there is no difference really, and the result was not significant. He expected that the aspirin resistance will affect the outcome of the patient, but it was not really. Really, the difference was not significant. And after the outcome really was major adverse cardiovascular event. For those who have aspirin resistance and those who don't have, really, they were not different, whether in the mean or the median. And long rank test was not significant. Despite that, so this is a long rank test, and the p-value was not significant. Despite that, Dr. Amin insists on doing Cox regression. So this is Cox regression. We enter all these variables. So there are really many variables, including aspirin resistance. So even the factor or the grouping which used in long rank test or in the survival table, he entered into Cox regression, and also entered the age, the sex, diagnosis, body mass, diabetes, heart failure, and smoking, and all of them really were not significant. All of them really, p-value, all of them not significant. And this is really what's called hazard ratio. The hazard mean just like the relative risk or S ratio for in logistic regression. So really, all of them, the The constant interval passes through 1. Yani they are not significant because they pass through 1. So they pass through the null hypothesis, and all of them, they are not significant. These are of course XP, يعني the معكوس اللوغاريتم مال B is معكوس اللوغاريتم الطبيعي equal the odds ratio. So this is here we call hazard ratio, and this is the constant interval for it. And really, all of them really they are not significant. They are not significant. Because why? Because already really here we didn't obtain a significant result really between those who have aspirin resistance or not. So really we didn't obtain a significant result. And even here we didn't. So the conclusion, of course, was that aspirin resistance doesn't affect the outcome. It doesn't affect MACE or major coronary event. So again, of course, this is a published article. Yani you don't need to obtain a significant result to publish the article. Sometimes also a result with negative result, yani an article or research with negative result also may be important. So this article really showed that aspirin resistance is not important. Doesn't affect the outcome, or does it affect the outcome until occurrence of a major adverse cardiovascular event, which means myocardial infarction and angina. Okay, so this is really how to show the result in an article. This is how to show the result in an article. You put a table, this table you put from SPSS, and also you put the graph, and you put also the result of the long-rank test. And if you do Cox regression, you have to put all these, just similar to what we have put in a logistic regression table. Remember the logistic regression table? Also, we put this in the, I think I showed you the for Dr. Fadwa. I show you the logistic regression for research for Dr. Fadwa. Contain the B and standard error of the B or coefficient, wall test, and the p-value, and of course the odds ratio and the confidence interval. Of course, in case of Dr. Fadwa research, there was some significant, like the age was significant, and also body mass index was significant. But in this research, we haven't obtained a significant exposure factor. Okay, so really in this data set we don't have factor really. We don't have other factor, but we show really clearly that there is a significant. So what I put in my article, I put this table, and I put the result really. I put log rank. I put here the p-value here, the 0.0. I would say p less than 0.001, p less than 0.001. Okay. Okay. So survival analysis is one of the interesting and advanced statistical analysis, and really it is a challenge for a physician to do it. Yani for Dr. Amin and Dr. Nasir, but really they were able to do it. Yani really, in more than one of their study, they have really more than one study in which they use survivor analysis. Okay, so I think as you see here, the survivor analysis here. So I said use Kaplan-Meier, in which there is log rank test, or use Cox regression. Really, what we said again here, we enter the same time, and we enter again status here, and we define status as 1. And then, of course, here we put the covariate, which are the group, and other. We should put other really, other factor. Really, we put other factor, not only group. Yani. We say okay. Again, I think we'll obtain something like. So really the it's significant, of course. The group is significant certainly, but it's only one factor. Usually should be put in Cox regression. We put more than one factor. So really group was significant, and this is the XP. This is the odds ratio, or the hazard ratio. Called hazard ratio. Okay, which is again significant. It is. I can ask again. I think I can ask for the constant interval. Let's see, ask for confidence interval. Yes, I can ask the confidence interval. So again, I analyze again. So this is confidence interval. See the confidence interval? It doesn't pass through one. Confidence interval, you know, the hazard ratio or the odds ratio or relative risk, when pass through one, it's not significant. So the null hypothesis for odds ratio or relative risk or hazard ratio in this case is one. So this doesn't pass through one. It's very easy from the 95 confidence interval of the hazard ratio is 2 to 10. So it doesn't pass through. It doesn't pass through one, which means it's significant. Okay. Okay. So this is a hazard ratio. It means this those who don't have who don't take combination of chemotherapy and radiotherapy, they are at risk. They are at risk of remaining of being delayed in remission or of not going into remission. So this is their hazard ratio. I mean that they are unlikely. They are less likely than those who take combination of radiotherapy and chemotherapy. They are less likely. Those who take only chemotherapy, they are less likely to go into remission. Okay. Okay. Of course, it is better in Cox regression to have more than one factor. Really, only we have one factor, only the group really. Okay. So really, I don't know whether you will use this in your thesis or not. Yani. I don't know really. Some might use it, might not use it. Yani. You might use it probably in pharmacology. I don't know. And you should really have follow-up. And without follow-up, really, and you should have follow-up. Without follow-up, it's a time series study. And if you follow your patient or your people, then you can do survival analysis. If you don't have follow-up, you cannot do survival analysis study. Okay. Okay, I don't know whether the subject is understandable. Really not easy, right? Not difficult to do Kaplan-Meier. Especially Kaplan-Meier, it's very simple. Very simple. But of course, you have to enter your data correctly. And sometimes also, I think Dr. Razvan or someone who a cancer specialist, I think is in the pharmacy. I think you have it in the pharmacy. He's a teacher in the pharmacy. He bring me a data also about survival of cancer patient. He has also time and remission. I don't know. He usually, of course, Dr. Razvan is genius, and he tried to do survival analysis. He was my student, of course, for many years, and now he's. I'm proud that he's a genius teacher at the pharmacy college. So really, he tried to make survival analysis, but there was an error really, and he came to me, and again, I tried really to do it. I don't know what is the error really. Probably he has an error in entering of the time or in the of the outcome. Really, we tried, but he was in a hurry, and he was making an article to present in the next few days in a conference. So really, I couldn't help him because there was an error mistake which I couldn't discover really. So sometimes really you need to spend time to enter your data carefully, to spend time to check your data, because really sometimes an error. We don't know what is the error really. I don't remember what's the error. Probably in the type of data, or probably really I couldn't check his. I couldn't fully understood why the error appear in his result really. But of course, if I enter group clear, I have no mistake here. If I don't have a mistake here, all of them in months, and also I write the outcome clearly, and I have censoring clearly. So really, I should have a clear result. I should have a clear result like this. So this really a clear result. There is no problem. There's no error here. But in case of Dr. Razvan, I remember something appear. Always there is error. I think there was something in the data, but really the time was very short for me to check the error in his data. And really, data set was extensive data set. Not as, for example, a small data set, you can check it easily. but for a large data set, probably you need time to check the error. Okay. Okay. Well, really, probably next week inshallah, we'll take non-parametric test. Of course, there is also in Cox, there is non-parametric and etc. There's parametric and non-parametric Cox regression. Next week we'll take non-parametric test. Probably next week, I think it will be the last week, unless you want other weeks for training. But probably I think next week, inshallah, if we survive, we can take. This will be the last hour, and according to our course, really, the module here next week will finish, and we'll take non-parametric test, and we'll finish our course. Okay. Okay. Also, really, regarding the midterm, I prefer that you send me by email. You can take my email from Dr. Burhan or from Kajin, and Kajin Hassan, I think she has my email, and send to me the result for the lead. Really, I want to show you. I want to see how you tried to analyze the data using test of t-test and using correlation. How you draw the data by how you draw the histogram. How you try to analyze your data. So I simply, it is just try to trial was a trial really. It was a trial. It will be a trial really for you. I prefer that you give me you send me your result until Thursday, and of course next week when we take the last session, we'll agree. We will make agreement about the examination, because the examination will be in the college. You'll bring your laptop and we'll sit in a hall, and then I'll give you the data. Probably if there's an internet, I'll give you through Wi-Fi, and then the data will be simple really. It will not be large data, it will be simple data, and I will also give you instruction. Any more, the objective, I try to make it more specific so that you don't need to go to the literature or to go textbook to see what is the matter. It will be clear. I mean, the examination will be simple and clear, and I think it will be easy to analyze the data. I will give you a small data set, which will probably I will try to select from this. I will try to select the data from this data set. This I'll give you the training modules. These are really, there are really a simple example which we can take it from here and we can use it in the exam. So the exam will be real, not virtual. Will be real, and we'll meet in the college one day, and we'll give you a data, and then we'll give you specific objective. Yani, certain table. You make a certain table and graph, and it will be clear, not that clear. For the lead, really, I wanted to see you. For the lead data, I want to see you what you can do. I want to see also. I want you to go to the literature, to the article. What should I do when I analyze data? When someone give me data, I go to the literature. I also said to student, give me the literature which is relevant to your research. So I go to literature. Sometimes I read a book, I read the internet, in order to understand the variable, to understand what is lead, what is ALDA, what is glomerular filtration rate, what is the normal level for serum creatinine for glomerular filtration rate. So I understand. I look to the articles. I look to the similar tables which have been produced in other research, and then do my analysis. So I wanted really for you to go and do something like this. But in the exam, the final exam, I will guide you. There's no need to go to the literature. I will say you what you will do. I will say you exactly the objective and what you will do. Okay, it will be simple, inshallah. Okay.
Okay, inshallah.
Okay. I don't know whether you have questions today. I don't know if you have questions really. Not easy, not difficult really. I used to be afraid from survivor analysis. I think it was complicated when you read a textbook. about survival analysis. It contains many math. Really, mathematics is very difficult, very complicated. So I was afraid, but when Dr. Amin and Dr. Rasir did it, then and they asked me to help them. It was really simple. I find it simple, really, not difficult to do it, really. But still, well, when you go to the logistic regression or to the survival analysis books, you find it's very difficult. You find it complicated. Really, we don't need the complication. We simply need to go and make the comparison, to enter the data correctly and make the comparison with log rank and draw the survival curve, and that's it. Okay.
Dr. Saad Al-Afun.
Bale.
I have a question, please.
Bale. Bale.
Generally in regression,
Bale.
In all regression, we have B value or the beta.
Yes.
So the B value, what is the exact meaning of the B? Because as you know, sometimes it will be shown as negative or positive also.
Well, the B value really is the B value is the coefficient. So, for example, here, this is the coefficient, the B value. As you see, last week I saw what is the equation. Really, the equation. Let's see here. We return to the. I think we can return here and show the equation. Of course, it's a simple equation, but can become more complicated. But the simple equation I showed really last week. So the beta really, the regression in general, or the equation in general, it is a simple equation. So this is the equation is simple. So Y really is a survival. In survival, Y is a survival. Or in another, for example, last week, for example, this was the height. So this is what's called the outcome, or the dependent variable. So the dependent variable in survival is a survival outcome. Survival is survival, whether someone die or survive, or remit or doesn't remit. Okay. So this is the outcome. This is the outcome, Y, or dependent variable. Now beta is a constant, really. Constant. Really, beta or B0 or alpha, sometimes B0 or alpha is a constant, which is usually it equals the value of Y when X is 0. When X is 0, it equals the value of Y. So it's a constant, really. Constant used in the equation. And then we have the variable, the independent variable, or the predictor, or the exposure variable. The exposure variable in simple regression is only one. It's simple regression, only one. We can also do correlation here between Y and X. We can also do what's called simple regression, is mean we have only one variable. So the one variable here, this one, is, for example, last week we said this is the height and this is the weight. So we use the weight in order to predict the height, the weight, or this is coefficient mean coefficient is معامل الvariable. So if I know your weight, suppose I have a scale. I don't have a height measuring instrument, but I have a scale, mizan. So I measure your weight, or you tell me your weight, then I multiply the weight by المعامل بالبيتا 1, or يعني coefficient of the weight, and add the constant to obtain the approximate height, obtain approximate or estimation of your height. Okay. Really, I explained that last week. So sometimes it becomes multiple regression, just like Cox regression. So in this case, there will be another variable like sex. So plus or minus, sometimes minus or plus, depend on the variable. So in this case, plus the variable which is X, male or female. So again, I will enter to predict your height more accurately. I will not enter your weight, but also enter your sex. So I said plus constant by the code for your sex. So for example, I coded male for 1. So I multiply the constant, which is after the coefficient, which is B2. In this case, it will be beta 2 by the code for your sex, which is male 1, and then again I add this the result for the sex and coefficient sex by coefficient of sex, plus this plus the constant to obtain more representative or more exact or more accurate measurement of your height. So again, really, it is the same equation for the survival, but I think it is contain more math theory and more mathematics. But it's the essential equation, really. Probably if we go to the end of the presentation, we'll find it for multiple regression. For multiple regression, let's go here, find the equation for multiple regression. I think at the end of the table, at the end of the, really, I showed that last week, really. For this is a multiple regression. Let us see multiple regression.
عفوا دكتور سعد. My problem is basically is to how exactly interpret in the regression of the beta. How you will interpret it. For example, is there any cutoff? Is there any specific value of that? For example, you said that more than that or less than that, it means that, for example.
Yes, of course, there is multiple regression. So this is multiple regression, of course. So really, for example, يعني the for the really, because it depends really on the variable. For example, for the height and weight, really here for the weight will be positive, because as the weight increases, the height increases. So really the coefficient will be positive. The coefficient will be positive. Okay. For the sex, yes, really, for the sex, really, the sex really would be 1 for male and 2 for female. So as we increase here, the height decreases. So here the coefficient should be negative. Why? Because female 2, the code for female is 2. So the coefficient should be negative, really. So being a female really will become shorter. Okay. So it depends on the coefficient depend on the variable, whether it affects positively or negatively the outcome. So here really in the, if I am doing the regression for the height, for the weight on height, really the weight, as the weight increases, the height increases. So the coefficient beta 1 is certainly positive. But for the sex, really, sex will affect the height reversely, because I put the male as 1 and female 2. So female is shorter than male. So really the beta 2 will be negative. So when you are a female 2, will be multiplied by a negative coefficient to produce less height. Okay. If I sometimes I reverse the code. Suppose I put like Dr. Fadwa or Dr. Wafa put say, well, I put the female one. Okay. So she put the female 1 and 2 as for the male. In this case, beta will be positive. So when you are a male, beta will be positive and you will have more height. So the estimation will be more for the male. Okay. So really it depends on understand on the coding. Really, the coding is very important. The coding really, I think sometimes really, Dr. Nasir Ispat, they are genius. Really, they have a problem with the coding, because they coded smoking differently. They coded smoking in a different way. So the reference for them was a smoker. They put the reference for a smoker. So really what happened to the result is that when it comes to smoke, because the code was put in a reverse way, they don't obtain the required result. Smoking decreases the risk of myocardial infarction. So they really wondered what they do. So when I came to study their data, I simply say, let us reverse the code. So it's simply what we have done, as we showed last week in the in logistic regression, we go to regression, and when really what they have done really when you have a categorical data, really categorical, really they have entered this, but they haven't changed the indicator. They let the smoker as indicator. So I simply change it. I said this one, and I changed the indicator as a smoker. So simply at that time they get a good result. They get the result that smoking increased the risk. Okay, so coding really is a problem really, and I have several really more than example. I can't talk really more about thesis I discussed really in Mosul really, especially when they enter the code wrongly. So the result really I heard of I can if you have time I'll talk about story. Really, I went to Mosul, and I was talking about a thesis which student really all discuss and take the mark. So she succeeded really. She already succeeded and took, I think, probably imtiaz. But her result really was reversed. Yani, all the result, and they find difficult to explain the result because it was really reverse to expected. And then the supervisor was finding the statistician. Really, the statistician was not a doctor, was not a pharmacist, was not really, he was an engineer. He was a civil engineer. Was muhandis, yani, really. So really, the engineer doesn't understand biological data. So simply he has put the code. The student give him the code, and really he didn't understand the biological data. So simply he put the code vice versa. And he put, as we see in smoking, he put the reference as the smoker. Okay. So in this case, really all the result of the student was reversed. And they put the explanation, and they discuss her, and they say, well, this is very strange. And at the end, after she discussed and succeeded, the supervisor was following the session, and he understand that he has put the code in a different, in a reverse way. So really, understanding the code, putting the code correctly, and understanding the code, understanding the variable, your variable, analyzing them before you do regression, before you do surveillance, analyzing them by descriptive statistics, understanding the relationship is important. And you can't simply just go and do regression. I sometimes, to do logistic regression, I spend 3 months to do logistic regression, to do understandable logistic regression. And it's not really easy to code the variable, because sometimes you may go and enter the code in reverse coding. So really, it is not easy for you and for me. Not for you, Dr. Burhan, also for me. The coding and how to understand the code and to enter the code into the equation is not really easy. Not easy. You cannot simply quickly do the regression, because you may simply code differently and you may get the reverse result. Okay.
Yes.
And as I said, Dr. Amin and Dr. Nasir, despite they are genius, they really spend long time trying to analyze their data, and simply they was putting the reverse code for the smoking and for other variable, of course. So simply when I just changed the code, I simply, they had a good result which they published, and they were very happy really with the result, and their article was published in an international journal. Okay, and it was not Corona, so they made Azima in Mat'am Malta on the research. Okay, and I was invited, and also other Dr. Sami was invited, Dr. Faisal was invited, Dr. Qasim was invited. So, but I think no, one of you was invited. Okay. Okay.
Doctor.
Okay.
So what I don't want to take so much time on this. Just one more comment, please. So it means that we have two things here in the beta, in the coefficients. First, we have a positivity and negativity, which is related to or correlated to the outcome with the
with the code,
with
yes.
the exposure. With the exposure,
I mean,
this
see
is
that the beta 2 for the male and female may change by changing the code. If you code the
Yes,
male
yes.
as 1, or if you code the female as 2 as 1, it will change. The coefficient will become negative or positive.
yes.
Okay.
And this is about the positivity and the negativity, doctor, and about the value, because as we know, for example, maybe it is 4, maybe it is 2, 2.5. So as much as the number is greater, it means that it is also related to the exposure and the value and the outcome.
Really, the beta itself is not really useful. What is useful is this XP, the odds ratio. Really, the odds ratio. Really, this one is the odds ratio. Really, or hazard ratio in survival, because hazard ratio really is indicate more risk. يعني. So this is really, I said this one mathematically. This is هي معكوس اللوغاريتم الطبيعي للبيتا. This is odds ratio. This is the powerful really of cost regression and logistic regression is that you give you the odds ratio. So you got the beta, but also you can get the odds ratio, which is probably I think Dr. Kaysar should have given that to you in the methodology. You talk about odds ratio and relative risk. So this is the odds ratio really and or hazard ratio, which means that of course the more the odds ratio, the more the risk or the more the hazard. And of course, it is important that the odds ratio and relative risk, they don't pass it through 1. Even if this is high, but pass it through 1. For example, if this is 0.9 to 10, even if this is 4, it passes through 1. 0.9 to 10, yes, it is high, it is 4, but pass through 1, it means it is not significant. Then in this case, this will be more than 0.05. It will be, for example, 0.7 or 0.9 to be not significant. So when this is significant, it means that this odds ratio should not pass it through 1, okay? Because 1 for the odds ratio is null hypothesis, okay?
Yes, yes. Thank you so much.
Of course, the more the risk, the more the relative risk or the odds ratio, it means that the more the hazard, or more the risk. The risk is more. Okay.
That's what.
Suppose that here we have maleness for heart disease. Of course, male have more risk. So the higher the odds ratio, it means males are at more risk of myocardial infarction. Okay, the higher the risk, they are at more risk. I mean, the probability of getting myocardial infarction for males is higher than for females. Okay. Okay, so this is the odds ratio or relative risk. Okay. Okay. Well, I think you have to return and read like Dr. Kaysar lecture about relative risk and odds ratio. Odds ratio and relative risk are well explained really in Dr. Kaysar lectures, and he explained them carefully really, the odds ratio, and also explained how to calculate them really, but he cannot really, estimation of the confidence interval very difficult in case control cohort study. You need to do that with a computer, but really this can be estimated from 4-4 table. If I can really estimate the odds ratio relative risk from a 4-4 table, but the confidence interval is difficult really. Usually need a software to estimate the of calculation because it include usually the natural logarithm يعني بها فد معادله وبها لوغاريتم طبيعي وشويه يعني حسابها صعب. فيجولي نحتاج الى الكمبيوتر in order to measure the confidence interval. Okay. Okay. So this is the essential equation for multiple variable. It's called multivariable regression. Multivariable. While the first one, if it's only one variable, called simple regression. But this is a multiple regression. Again, if it's only surveillance, it's only the group, and the survival, it's called log rank test. But if it is more than one variable, it's more than one predictor, there are many factors. It's called Cox regression. Okay. I don't know whether you have other question. I will stop sharing really. not really, not difficult subject. If you don't want to understand the mathematics, it is simple. If you want to understand the mathematics, really not easy. And if you go to a textbook for survival analysis or logistic regression, you find there is a lot of mathematics, which make the subject difficult. Okay. I don't know whether you have questions. Next week we'll take, as you said, the non-parametric, and probably we can finish our course. Okay, inshallah. Okay. Okay. Any question? Another question? Okay. I think we'll end that. بخاطر هوا موفق إن شاء الله.
قال تجي إن شاء الله دكتور ساتشاو.